there, I'm Natalia from the ACM Student Chapter Munich, and I would like to welcome you to our very first digital meetup. Today we will have two great talks on imbuing AI with knowledge. At first, I will give you a short introduction about who we are, and I will hand it over to my colleague Johannes, who will moderate the discussion. So, we are a student organization. We're students from computer science of LMU and TUM in Munich. We have very different backgrounds, but we are all fascinated by machine learning, and that's why we organize meetups to this topic, meetups and other cool events. We have always great food at our meetups, but unfortunately not today. And if you want to stay tuned to our upcoming events, you can follow us on Facebook or LinkedIn or Meetup. Actually, the Meetup page is the most important one because you will get the newest updates on the spot when we publish them. So today we will have two great talks. Our first talk will be held by Felix Weitkämper. He has a Doctor of Philosophy from Oxford, and currently he's a research fellow in programming and modeling languages at LMU. And his talk will be about statistical relational AI. And the second talk will be by Professor Volker Tresp. He's distinguished research scientist at Siemens and honorary professor at LMU. And he will talk about machine learning with knowledge graphs. And now a little bit about our schedule. The first talk will last approximately an hour with the discussion. And one important point about the discussion, please put your questions on Slido. We have a special tool on Slido. You can find the link in the video description below. And after the first talk, we will have a short break. And then we will have the second talk, which will also last approximately an hour. And the same rules with regard to the questions apply there. And finally, we will have an open-end socializing on Discord. You can find the link below as well. And we will have two channels there. Each is dedicated to each of the topics, so you can choose which one you want to join, or you can join both. And there is also a random channel. So that's it from my side. I wish you fun, and yeah, Johannes, the floor is yours.
Thank you very much, Natalia. Dr. Weitkämper, if you could already share your screen, please. Well, hello, everybody. Our first talk today is by Dr. Weitkämper, who I know for a seminar I attended of his this semester. Dr. Weitkämper will be talking about statistical relational artificial intelligence, a topic that is very much in line with our focus in the student chapter on machine learning and artificial general intelligence. And I will first start with a short introduction. Dr. Weitkämper, you studied maths at the University of Munich, so you're actually on your home ground here. Then you went to Oxford for your PhD, also in mathematics. Now, since this semester, you're a research fellow who has switched over to computer science, again at LMU, and are currently working on your habilitation under the supervision of Professor Volker Tresp. So we actually have a student-teacher relationship here in our speakers today. Your focus is on mathematical logic, and more specifically, model theory for statistical relational AI. This is a subfield of AI that is can be described as one of the deductive paradigms. So we have knowledge bases or first order logic in most cases, general logic, that we use to reason about the world based on a set of facts. And in the most recent years, these deductive approaches have been largely overshadowed by the more inductive methods such as machine learning, but very much has happened within the last few years. And today we will hear about this development in the deductive field of AI from Professor Weitkämper. We're really excited about this because one of our focus in the chapter and my personal specialty is artificial general intelligence, so human level AI. And in the most recent years, it has become more clear and clear, so I'm talking about 2 to 3 years, that machine learning, so simply building bigger artificial neural nets and throwing more data at them, probably won't give us that artificial general intelligence, a human level AI. So your work, Dr. Weitkämper, is on exactly the boundary between inductive and deductive methods. You're trying to synthesize them. So it may be one of our great hopes actually to getting towards AGI. So we're really excited today to hear about what happened in the last year in the fields and what are your plans for the future. Thank you very much for joining us. The floor is yours.
Thank you very much. And thank you very much for the flattering introduction. I must say I have not officially started my habilitation project yet, so that is still up to the university bureaucracy. However, I have already worked in statistical relational artificial intelligence, and I would like to make this talk in 2 parts. First, I would like to give a brief introduction on intelligence and artificial intelligence, just to take a step back and to see what we are actually talking about and why we should imbue it with knowledge. And then I will give an introduction to statistical relational artificial intelligence, which will be kept brief and informal, because I don't want you to spend your evening brooding over mathematical frameworks. And then I will move on to some current projects that we are doing here in Munich, both practically and theoretically, both to give a flavor of what statistical relational AI can do and is good for, as well as ideas of what is happening right here on your doorstep, at least your digital doorstep today. Right, what is intelligence? This is not a strict claim in line with modern philosophy, but it is the consensus within the artificial intelligence community. Intelligence is generally divided into 2 parts. It is learning from what we experience and reasoning from what we know. Often, this is seen as quite a strict dichotomy. There is machine learning, which addresses the first part, learning, and then there are deductive systems, there is expert systems, there is also automated theorem proving and so on. There is data log and deductive databases, for those of you with a connection to the database community, which are considered parts of reasoning. However, I would like to make clear that there are, independently of anything we are doing here, clear connections between these 2 fields. Any learner, be it as pure a machine learner as it might be, such as a neural network, is useless if it does not make at least predictions from what it learned to things it now experiences, to things it is exposed to now. This is akin to some sort of instinct in traditional parlance. It takes a new situation and somehow aligns it with things it has learned before, and it gives a prediction or a possible approach or a decision or whatever the case may be. This is different from reasoning because reasoning makes clear deductions. You know A, then you know that A always entails B, and thus you deduce that you also know B. However, there is a gradation here from learning to reasoning. And there is a gradation from instinct, the making decisions on the basis of what one has learned to reasoning from what one has. And this goes all the way from the simplest propositional calculus to sophisticated higher order logic via everything in between. And a lot of computer science looks at these gradations. So while this is not cutting edge philosophy, it is very much in line with what has traditionally been seen as making a human. A human was seen in classical, let's say 16th, 17th, 18th century philosophy and earlier as being elevated from the beasts, the other animals, by reasoning. While often it is also seen that instinct, what is needed to make use of learning, is a prerogative of animals, including humans, over inanimate beings. Now, I could have chosen any quote from 2000 years of philosophy to illustrate that, but instead I've chosen a poem by my absolute favorite poet, Alexander Pope, an 18th century English wit and intellectual. For the literature buffs, the quote I'm about to put on is from Epistle 1 of his Essay on Man, and it is here given in modernized spelling, but is of course to be approached with the usual caveats of being an 18th century text. How instinct varies in the grovelling swine, compared half-reasoning elephant with thine. Twixt that and reason, what a nice barrier, for ever separate, but for ever near. Already here, in this 18th century text, which is a marvelous piece of work, the Essay on Man, rambling on about everything and nothing, one already sees this idea of a gradation that will accompany us also to an extent throughout the talk when we have different frameworks that have different powers to reason over different things. But what does that have to do with knowledge? Why do we need knowledge for reasoning? Well, there is not much point in reasoning if we do not want to just list trivial tautologies if we do not have knowledge. All this was already well known to Pope. Say first, from God above or man below, what can we reason but from what we know? So imbuing AI with knowledge and representing this knowledge in a way that is accessible to the machine and to deduction is crucial if we want to make use of any reasoning. Now, I'll give you a brief overview of artificial intelligence from the lens of statistical relational AI, so precursors of statistical relational artificial intelligence. The earliest artificial intelligence was purely symbolic. It is based on reasoning. From given facts, knowledge, and rules, new knowledge is derived. These rules were traditionally handcrafted by experts. That means they are not learned. In the original pure symbolic artificial intelligence framework, they are not learned. People who know a lot about the domain in which this artificial intelligence should function put their knowledge into a machine-readable form, and then the machine makes deductions based on this knowledge. This is still very much used, for instance, in fields of assisting medical diagnoses as well, where doctors or healthcare professionals put their knowledge on diagnoses and so on into a machine format to aid with diagnostics. Interesting here is that both the facts and the rules already quite early. For instance, there is the logic programming language Prolog, which developed since the 1970s already, and it can deal with highly complex facts and rules. For instance, see the following example, which we will see in a varied form later. Let's say there is a house H. Then you could have the following chain of events. If the house H is on fire, we can write that as a predicate, burns, open bracket H, close bracket, and person P is a neighbor of H, a binary relation, neighbor P of H, and person Q works as the local fire warden of Q, then P will call Q. There would be the relation call of P, Q. This is quite complex knowledge because you have relations between different entities, all of whom have different positions in this situation. And one sees immediately here the relation to relational databases. relational databases also have these complicated relations with many different arities. Database schema can be quite complicated, and that has their roots around the same time. This is highly expressive. We can express lots of different logical deduction. We can express recursion, whereas many things have been worked through in this, from abductive reasoning to deductive reasoning and so on. However, there is a major limitation to this, and that is dealing with uncertainty. The problem with symbolic artificial intelligence is that every rule is required a priori to be always true. Otherwise, you cannot include it because you will just deduce rubbish. This led to a crisis, the AI winter of the 1980s, and to the rise of statistical artificial intelligence. I said it is one of the main present-day machine learning frameworks. Of course, there are neural networks, but they don't really play a role in the knowledge representation that I'm about to give, and therefore I will turn a blind eye to them and we'll look at statistical artificial intelligence. The problem here is the following. It seems an obvious solution to the uncertainty problem to use probabilities. That is because probability calculus, probability theory, statistics are mature fields with a lot of results and a deep theory. So why can't we just harness that for artificial intelligence? Well, originally, integrating probabilities was considered impossibly complex. Because consider this. Let's say you have 100 facts. That is actually a laughably small amount for a full artificial intelligence framework. If we do not assume anything on their independence, the probability of any one of these 100 facts to be true is going to depend on all 99 other facts. But that means we would need to make a table with 2 to the 99, that's around 10 to the 30, an impossibly large number, of different probability values. This was absurd, it did not get anywhere. However, in the 1980s, and this became popular really with Judea Pearl's book, Probabilistic Reasoning in Intelligent Agents, graphical models were introduced. The classic ones are Bayesian networks and Markov networks, also known as Markov random fields. I'm going to focus on Bayesian networks here for now. These are graphs, either directed acyclic graphs in the case of Bayesian networks, or undirected graphs in the case of Markov networks. And every probability of a formula which takes a node, so the nodes are labeled with facts, and the probability of a fact on a node being true depends only on the truth of those nodes immediately connected by an edge. Suddenly, we have a huge number of independence assumptions for free, while we can still really transparently show what we want and what we mean. However, this worked beautifully, but the main focus shifted from reasoning about complex relationships to facts, learning the probabilities of simple properties. Simple in the technical sense of non-relational, just a fact. It burns, it calls, no relational information here. And then statistical relational AI came about from around 2000 onwards, attempting to put those two paradigms together. Now, since the symbolic community and the statistical community were quite separate, they grew together from both directions. One group intended to expand logic programming to deal with probabilities, where the other wanted to extend graphical models, like Bayesian networks, to deal with relational information. However, because the problem that Pearl was faced in the 1980s still applied, even if you expand logic programming, for instance, it needs to be based on a somewhat like a Bayesian network or something formalism. So actually, these are quite close. A big difference in the frameworks is, there are many of these frameworks, is how they parameterize the relationship. So in some cases, you have actual probabilities. So you have a Bayesian network, we'll see that in a minute as well on an example, where there are real probabilities on the arrows. Some have tables and some have weights. So a formula that is weighted stronger, a stronger edge has a greater influence on the probability. And here, both learning and reasoning have their own literature and are both equally important. So this is a very fruitful research topic because you really now have the interface of learning and reasoning. I'll give an example. So this is a abridged example of what I had mentioned earlier. Let's say I have a house H. If the house burns and X is a neighbor of a house, then X will call with certain probabilities. Because X might not be home, then X will not call. Or X might hate the owner of H and couldn't care less, or is even quite gleeful that his house burns down and will not call. And so on. The difference between this and a standard Bayesian network, so we have variables H here and relations. Variables H and X and a binary relation here, for instance. We now instantiate or ground this network in any given domain of houses and people. And then it might look like this. So in this case, whether Anna calls depends on whether the house 1 burns, whether the house 2 burns, and whether Anna is a neighbor of house 2 and a neighbor of house 1. These are the 4 pieces of information we need. Now one can imagine that as we get huge domains, a city for instance, this becomes very hard to glance with a naked eye, while this one single representation in a lifted relational way is still quite easy to parse. Well, very easy in case of only 3 nodes, and it will remain 3 nodes, regardless of how many we have in the grounded Bayesian network. A similar example, just to show that we can also have propositions. This is adapted from a very classic example called friends and smokers for obvious reasons, because these are the 2 things it mentions. And the example here is you have X. X is a friend of X is my friend, and X smokes. And depending on how many friends I have that smoke, I have a greater probability of being a smoker myself. For some reason, this has become a huge textbook example. I think one of the reasons is that the whole smoking and cancer, normally I have another node here causing cancer, was quite controversial in statistics, and therefore statistical AI took this as a paradigm for how statistics can help solve problems. And again, we can instantiate it. If we have a domain consisting of Anna and Benjamin, then my probability of being a smoker depends on whether Anna and Benjamin are my friends and whether Anna and Benjamin smoke. So far, so reasonable. Now, why would we want a statistical relational AI like that? First of all, it is highly expressive. That means we can write anything that we could write in normal logical systems and whatever deductive system we have. And we can also include knowledge on probabilities. We will see later in one of the current projects that we're working on that this expressivity can be really important when we want to model human reasoning on some domains. Because on some domains, humans very fluidly combine abstract reasoning with probabilities. It also supports a high level of reasoning. This is quite interesting, and we'll also see an example of that later. And 2 ways in which it supports high-level reasoning, for instance, is that it is very good in supporting abductive reasoning. Abductive reasoning means you observe a result and you reason about the possible causes. It all sounds very abstract. Again, I'll mention it later. But also counterfactual reasoning. So we can model a behavior pattern, a general behavior pattern that we have gleaned from a current situation, then change the outside parameters and see how the behavior under the same relative behavior pattern would play out under the new parameters. Again, we'll see an example of that later, and this can be very powerful. Whether this is true counterfactual reasoning can be debated, and there is a philosophical as well as a computer science point about this, which I will not have time to go into, but it is a higher level of reasoning than either purely symbolic or statistical approaches have. Now, there are other 2 points which I will not use particularly later, but which are very interesting. The first one, fixing symmetries in learning, is a particular point in machine learning. If I am learning a Bayesian network, let's say I'm learning this Bayesian network using machine learning approaches, then I will use some data and then I will learn it. And it could be because of random deviations in my data. It is quite likely that the edges from house 1 and house 2 to Anna and Carla will not have equal weights, equal powers. That is just due to quirks in the data. But since the Bayesian network does not know that Burns of house 2 has anything to do with Burns of house 1 a priori, if we have no lifted relational backbone, it does not think anything is amiss. If we learn this relational lifted network instead, it is very different. Because if we learn this network, then we have to agree on one weight influence factor from burning to calling and one from neighbor to calling. So we enforce or fix symmetries in learning that we believe are appropriate to the domain. On the last point is also very interesting. Explainable AI has become a big thing recently, so that humans are able to read or somehow glean information from the representation rather than just machines. And this is interesting for two completely different reasons. I'll just give two examples. One is high stakes decisions such as medical domains. I do not want to trust a black box machine. I want to be able to see what it does and see if it makes sense. The second part, for instance, is when AI should assist humans. A classic example, which I will also mention later, is a game. A chess computer is of greater use, for instance, if it is able to explain its reasoning to a human who can then use it to become a better chess player. Now, this is still reasonably human readable, but imagining a whole city with in Munich, over 1 million people, over 200,000 houses, this will no longer be easy to pass by a human. This is. Right, so why do we not just do everything in statistical relational AI? Because statistical relational AI can do everything. Well, there is a high computational complexity. If we brute force methods, i.e. we just run the inference on this grounded network, and we do not care about about the lifted network once we made it, and we run all our algorithms on the ground level, this is clearly exponential in domain size. It's particularly bad because they have what is called a possible world semantic, so I consider the probabilities as probabilities of possible things which could be true, and that blows up exponentially very quickly. So this is particularly bad. A more subtle point is the scaling behavior. This can be unfavorable. And we will see that, I will come back to that in a minute, but it means that even if we understand what this means when we have Anna, Carla, house 1 and house 2, and we fix the weights, if we have a weight parameterized model, for instance, on both of these arrows, that does not mean that if we scale this up to a city, these weights would mean the same thing, and that's a problem. I will come back to that later because that is actually a focus of my own work. Now, this is as brief an overview as you will get, because I would now like to move on to talk about some current projects. These should just give you a flavor for all the things one can do with statistical relational AI and what we do in Munich. Now, who is we? We is a team of highly motivated and skilled undergraduate students, so bachelor students who are writing their bachelor theses under my supervision, as well as a master student in biology. And I will mention them as we go along. So the first example of what we are doing right now is modeling a COVID-19 outbreak at the university. This is joint work of my students Ella Meyer, Güneş Teker, and Beatrice Sabu, and myself. We're using statistical relational AI approaches to model the impact of that teaching would have on the COVID-19 pandemic. This was my brainchild from March-ish, when the discussion was still raging whether we would have teaching in the summer, and I thought statistical relational AI would be perfectly suited to assist us in answering these questions. It allows us to combine real data from the mathematics and computer science departments of the university, why we chose these, is not really because we are biased, but because the university has a system called Uni to Work, which is used in mathematics and computer science, and whose data was available, incredibly helpful staff there, and they helped us anonymize this data and use it in conformity with data protection regulations. And we can combine this real data, that's data of which student took which lecture when, with epidemiological models of infectious disease dynamics, such as the SIR model. This is where the biologist, Kaelin's son, a master student in biology, has really helped us. And as a result, we hope to obtain a transparent estimate on how the spread of disease would be if the students behave the way they did in the last winter semester. So if they behave the way they did in the winter semester 2019-2020, if this would be imitated in the following semester, as it might still be the coming winter semester, I think everything is up for grabs at the moment, then how will disease spread? And we can model this quite beautifully. However, we can do more than just model and use data. This is, of course, already great, but what we really want to say, well, what if we only allow lectures up to 100 students? Well, in that case, lecturers would have to offer more lectures, for instance. Students would have to, and students might have to choose some lectures less because, okay, well, this, maybe they think this semester we'll get less ECTS points and more next semester and so on. So we would also need to know how flexible are students in how many ECTS points they take, for instance, how many lectures they visit, and how flexible are lecturers and how many courses they offer. And this is what I meant with counterfactual reasoning. These tendencies, the tendencies to offer courses, the tendencies to take courses, can be modeled using a statistical relational AI framework. And then we can impose constraints on these possible worlds, like only lectures with at most 100 students allowed, or only master teaching, or things like that. How would the infection progress then? And this is really quite an exciting question, because all these options are actually still real options, and we could give real data-driven answers to these questions. And this what-if reasoning requires that we have a way to represent tendencies and behavior that we can extrapolate. And we need statistical relational AI to help us do that. Now to something completely different. With, at the moment, only one other student, Ming Li, I'm working on making an artificial intelligence for the card game Bridge. This is quite a neat problem because it is one of the few games where AI is quite far from outperforming human players. This has several reasons. The main one is that it is a cooperative game of imperfect information, where it is crucial that the strategies devised by the cooperative are transparently communicated to the opponents, and there are rules to enforce that. This makes it quite difficult to approach with standard deep learning methods. Why is it particularly suitable for statistical relational AI? A, because of the expressiveness. We need probabilistic calculation, and we also need quite sophisticated reasoning, because this is how a club player in Bridge would approach a standard bidding problem. My partner's bid of 1 spade shows me that she has 5 spades and a certain strength. Knowing my hand, a full game in spades must be the correct contract. One could easily replace must be there with is highly likely to be the correct contract, therefore I will bid it. And this sort of reasoning works quickly and efficiently at the card table for humans, but it is actually quite involved for a machine. One needs the full power of probabilistic calculation because one needs at least to have a measure of what is highly likely. And then you need this, which is called abductive reasoning. My partner's bid of 1 spade must have had a cause. This cause is a certain pattern in his hand. So I have to reason from the result, the 1 spade bid, to the cause, and then I have to combine this with information about my own hand, perform a probabilistic calculation and arrive at the correct contract. And this sophisticated reasoning is something statistical relational AI is very good at. And it also gives a full trace of these deductions. So it could explain to a beginning bridge player exactly the thought process that would be behind a bid, which is very exciting for an artificial intelligence approach. Right, now, these are the practical applications that I'm working on together with my students at the moment. However, it also seems highly desirable to mitigate those challenges, the high computational complexity and the awkward scaling behavior. These are huge barriers to mainstream use of statistical relational AI. And therefore, I'm also working on this. And in fact, the methods of model theory and probabilistic logic that I am personally acquainted with come very in handy there. Now, I also have students working on this. My team here consists of Ramona Fabri, Dimitri Ravdin, Michael Vogt, and Yiming Wang. And we are working on scaling and behavior on large domains. By considering this limit behavior, we hope to tackle two parallel challenges together. A, how can we evaluate a framework on large domains without using excessive computational resources? This is the computational complexity problem. If we manage to understand the limit behavior, so the behavior on very, very large domains, then we can see, well, maybe already from 1,000 or 10,000 data points, it is basically at its limit. And then we can just calculate on the understood limit behavior, and we do not have to ground. But also, if we only have a small domain of learning, the classic example is a randomly sampled set. This is a standard statistical approach. How can we transfer this to a larger domain of application? Take a randomly sampled subset of a social network, for instance, and we would like to transfer this to a larger domain of application. In general, the likelihoods computed by the framework change drastically as domain size changes. And annoyingly, they tend to converge to a fixed value. And that, unfortunately, is completely independent of the probabilities or weights in the Bayesian network that we have supplied or that have been learned. Now, there's no point in learning them in the first place if they are not going to matter. So if we just increase the domain size naively in the two examples that we have seen here, they will both limit to 1. Look here. If we have lots and lots and lots of houses, a huge city, and lots of people, if we just have raw probabilities for each individual here, the bigger the city, the greater the chances that a house will burn. And annoyingly, we would also have a fixed probability that you are a neighbor of any house. This is unreasonable. You cannot, there are 10,000 times as many houses, then you do not have 10,000 times as many neighbors. But it would mean that you will always be the neighbor of one house that burns if there are only enough houses. And this is not what you actually want to model. The same here. If there are many people, each of which have a certain probability of being my friend, each of which have a certain probability of smoking, then I will always have so many friends that smoke that these weight factors will always add up in such a way that I will end up with a 100% chance of being a smoker. This is not adequate to our intuition of how these domains should function. Therefore, this is of course a difficult question, so this is not a question which is an easy and one-size-fits-all solution, but there is an approach. And one of these solutions is replacing the dependencies on numbers with dependencies on proportions. So let's think about this for a minute. Let's say we have the example of friends and smokers. Really, it would make a lot of sense to say, I am more likely to be a smoker myself, depending on the proportion of my friends that smoke, not the number of my smoking friends. This is much more closer to our intuition. And we can actually prove, and I have recently published a paper on this, that on weight parameterized relational Bayesian networks, these are called relational logistic regression networks, it's just one particular framework for statistical relational AI. This is theoretically guaranteed to lead to benign and parameter-dependent limit behavior. So we can prove that as the domain size reaches infinity, we still have a easily calculable and parameter-dependent behavior in the limit. That is wonderful. In fact, to my best of my knowledge, it is the first framework where this has been theoretically proven or even experimentally conjectured for. But is that really always the intended meaning? If we go back to the example of having houses and neighbors, surely whether I call should not depend on the proportion of houses in my neighborhood that burn. I still want to say, if any house burns, I have an 80% chance of calling. Here instead, we have a very different limit behavior, that of saturation. I can't have more than 8 neighbors. And if the domain size increases, my probability of being the neighbor of a given house decreases drastically. And how about the other frameworks? These weight parameterized relational Bayesian networks, the relational logistic regression networks, are not particularly popular in practice. They are one, and not even a very popular one, of many frameworks. They have some disadvantages. They cannot cope with loops because they are absolutely dependent on directed acyclic Bayesian networks, and they are weight parameterized, so you cannot easily read off the probabilities. There are many disadvantages. It would be great if we could do this for the more mainstream frameworks like Problog, which is a logic programming language that also can deal with probabilities, or Markov logic networks, which are the main relational graphical model that is used. So there is still a lot of work left to be done. In my future projects that I will also try to tackle for my habilitation, I will also try to look at the semantics. So what does it really mean? So what does it mean if I depend on a proportion? Then I don't really have possible worlds anymore, in the sense that I can consider each fact separately, but I actually have a proportion in my system. So the semantics is different. Many exciting topics here. And yeah, I really hope that this could help make statistical relational AI better understood, more widely deployable, and theoretically maybe a bit more sound. Thank you very much for your attention. I hope I didn't keep you too long, and I would be glad to take any questions that might have arisen.
Well, thank you very much. Everybody in the stream, you're now open to pose questions. I myself already have one, which I will now quickly put in front. You see a good future, hopefully, for statistical relational AI, and seeing it make a comeback in the face of the lowering popularity, maybe, of deep learning approaches, as they seem to hit bounds in some places. So could you maybe also present some of the past highlights that have been produced by symbolic AI? Because in the most recent memory, all the great AI breakthroughs were some deep neural nets. So what were the major, I don't know, is there some kind of AlphaGo, or some Watson winning Jeopardy, but for statistical relational AI?
Well, that is a difficult question. So statistical relational AI as such has as of yet remained an academic pursuit, mostly. However, academic does include great successes, for instance, in genome analysis. So mainly in bioinformatics and genetics, this has been used. Also in chemical compound analysis, so more heavier industry, in this case research, so heavier research results, and perhaps less so snazzy, popular results. The reason it works well for genetic, it also works quite well in the medical domain, but the problem with the medical domain is that they, of course, have very high standards before they deploy anything in practice. But the reason it works very well for genetic data is because genetic data is beautifully structured. We understand DNA code. There's a genotype-phenotype relationship. Everything is beautifully structured and screams for a more structured, symbolic approach. And that really works well. So apart from that, the problem with anything on a greater scale is really the lack of scalability. And that is really hindering attempts at larger deployment, and I cannot claim that our attempts at a bridge artificial intelligence are anywhere near AlphaGo. So no, I'm sorry to disappoint there to an extent. I think it is also a very young and slightly underfunded area of research, at least in Europe. It is more popular in the United States, and there is a large research group in Leuven working on Problog who come from inductive logic programming. Inductive logic programming, incidentally, which is these actually learns rigid, non-probabilistic, complete logic networks in a machine learning setup that's also really interesting, is widely used for planning, for instance, planning applications and scheduling problems and so on, but also all rather dry stuff.
So following up on this, we actually have a question from Slido by Anonymous.
Yes.
Dr. Weitkämper, in your opinion, how much time and research is still needed for statistical relational AI to become full-scale deployable in the industry?
That is a difficult question. One might want to bounce that also to Professor Volker Tresp later. I think he will also have something to say on that because he is actually from the industry. I think it would be facetious for me to claim what the industry still requires. For it to be deployable, for instance, let's look at this example. Let's look at our example of what we are doing to model the corona outbreak. This is clearly not industry, but it is an interesting application which is not really obviously achievable in a comparable way with other approaches. For this, there is sufficient resources to reason and learn over the larger data sets that we have, which, if one takes, for instance, being classmates, then we have a square of the tuple relation. We do have around 6 million tuples. However, already there, we do not, in order to conserve computing power, we need to use clever scaling or other tricks, which I think require a large expertise to use. It is not basically I load a Weka package, I click, or I do some Python code, I just load a package and it chooses automatically the correct scaling approach and it gives me something. There is a lot of thinking involved into cracking this. Then I do believe it scales to this level of data sets. But if only researchers in statistical relational AI are able to use it, that is a barrier to deployment.
Okay, well, following directly up on your COVID-19 example, we have another question from another anonymous. Do you think the modeling results of the pandemic outbreak are reliable enough to be used for decisions affecting massive people? I expect this is meant to be affecting a great amount of people already.
That is an excellent question. The reliability comes from, to an extent, from traceability and from the transparency of our assumptions. So, for instance, the assumptions, we do not have to make assumptions. For the counterfactual reasoning that we consider here, we would. For the general modeling, we do not need assumptions on how students would behave because we use the data raw. We do not really have to learn or process on this data. We use it as evidence. However, of course, we have to input the epidemiological knowledge. And the epidemiological knowledge is very shaky. As one can see, there were studies done in Oxford and in London at the very beginning of the crisis, and the Oxford study said, oh, 60% of British are already affected. So by our modeling, this should be no problem, and we will reach herd immunity in no time. Alas, that was not to be for the United Kingdom.
Oh my.
And the London study came to a completely opposite conclusion, both by renowned epidemiologists. The advantage that we have on this front is that we make our epidemiological parameters completely transparent. They are in the code. Indeed, one can even input them as parameters. And we could model, well, under these and these and these different conditions, these would be the outcomes. We do not claim to know the epidemiology because epidemiologists don't. But we can claim that we can give a range of outcomes. We also implement this not only on Markov logic networks, one framework, but also in a different framework in Problog to compare the results. And if they are widely differing, that would have implications on the reliability of these statistical relational models in general. So this is something I'm personally very interested in. So we make two completely distinct models using distinct frameworks and see to what extent they agree given the same data.
That's interesting.
That's
Are
our
there already predecessors to such approaches using such symbolic AI methods for disease outbreaks? Do you have any historical research to work on, or is it a completely new idea?
There has been a limited study on a tuberculosis outbreak that has been performed in the very early years of statistical relational AI around the 2000s. But it works very differently. That tries to predict risk factors for tuberculosis. So they try to use it to see, well, if this person has a certain income class, or et cetera, how much at risk are they of tuberculosis? So that awareness programs and so on could be better targeted. For all I know, this was successful, but it was never acted on. And that is all we had to go with but this is also because the technology has not been here for that long. The technology to deal with even a 6 million tuple set has not been there more than a couple of years ago. And frankly, epidemiology has not been at the forefront of research remotely as much, at least among computer scientists, non-epidemiologists. And if there had not been a coronavirus outbreak, we would probably not be doing this now either.
Very interesting. So your paper can actually become the classic that people then quote when they come into the situation.
Well, the hope is that at least it is interesting not only to computer scientists. So we try to get data which is interesting to computer scientists as to the limits and scope of statistical relational AI, especially on the counterfactual reasoning side, but also of sufficient interest to epidemiologists that they consider, because at the moment they use no artificial intelligence, as far as I know, for the actual disease modeling. They use it for many other things. The actual disease modeling is done on a purely statistical, probabilistic, algorithmic way, not using artificial intelligence as far as I know. So I hope that this would also open the door to epidemiologists using artificial intelligence approaches more widely. But that would, of course, is a dream. Whether this will materialize is never clear.
We have a fitting question for this on Slido. Dear Weitkämper, what do you think would it take to use statistical relational AI to better understand complex system interactions and cascading effects? So I believe with complex system interaction and cascading effects, especially the cascading spread over disease can be named, and the complex systems that are our societies where diseases spread.
I think this is a perfect use of statistical relational AI, and the only barrier is the large amount of data, although there is usually less data required than one might think. The problem is just that you need to know exactly what your domain is. So doing this in general, modeling the world spread of coronavirus, would of course be futile, because also you have lots of parameters like locality. Maybe that's what meant with complex systems as well. You don't have you would need graph modeling methods and so on. We're also trying to integrate clustering methods, for instance. We want to cluster the students by the semester they are in. Well, we do not actually know which semester they are in because that got lost in the anonymization. So we will recover those, hopefully, through clustering. And this is also a way of scaling. We can then use within cluster and between cluster separately, drastically reducing our degrees of freedom that we need. So, and the data sets in every case, because we don't have n squared, but 1/10 n squared, 10 times basically. So that is another way in which a complex system could be broken down. And this has not been done yet, as far as I know at all. So pre-clustering for statistical relational AI has not really been researched, as far as I know, with a specific intent of making data more manageable for a statistical relational AI learner and reasoner. And Günesh Tekke, one of my students, is investigating exactly that.
All of our questions on Slido are addressing the scalability problem. So
yes.
I will pose two of them that might be answered in a similar context. So the first is, could quantum computers help with the scalability of the statistical relational AI applications? And the second question is, would you think that given the complexity of the problems described and a probabilistic nature, would approximation algorithms be a paradigm that could improve?
Right. An approximation algorithm, if I already have a probabilistic model, an approximation algorithm would only really help, as far as I know, I'm not an expert on this, on approximation algorithms, but my gut feeling is that it would only help to tame the complexity if it means assuming more independence. So we assume things are independent where they are not. So this sort of approximation, like a naive Bayes classifier, is very fast, for instance. Why? Because it assumes everything is independent when it isn't. Yes, but we already, through Bayesian networks, try to do this as much as is feasible. If we assume more independence, I think it's hard to gauge the loss of accuracy that we would have. And without bounds on the loss of accuracy, I don't really, its practical usage seems limited. I might not be understanding the question correctly, though. And for quantum computing, unfortunately, frankly, I'm not sufficient expert. The problem with statistical relational AI is that they are complex systems, right? They are themselves complex. And quantum computing so far does not really work with, I don't know, full-scale Python or Java infrastructure, etc., etc. So I think that's maybe, if one could do SAT solving, this is a very famous problem in theoretical computer science, which also has impact on AI. So counting, for instance, how many models a simple propositional formula has. If that is, in a sense, the bottleneck, if SAT solving would be improved through quantum computing, that would be great. But that's a problem far beyond statistical relational AI. If SAT solving could be done as a paradigm intractable problem on quantum computing, then that's probably Turing Award worthy in itself.
It's funny, just today I held a tutorial where we covered SAT solving. It's a fitting topic.
So what's your opinions on SAT solving and quantum computing?
I don't have an opinion on the connection between those two, but I have to add something, because Professor Tresp on his website actually states that quantum machine learning is one of his current research focuses, so maybe he can later also go in that direction. What do quantum computers change in the field of AI?
But do also ask about the statistical relational AI in industry, because I have had a chat with him about that before. So I think he will have something to say about that too.
We still formally have 10 minutes left. but we already posed you so many questions. We still have some on Slido. Are you still willing to take it?
Absolutely. I deliberately, you slightly scared me into shortening my talk.
Sorry.
So no, I think it's great. I do think as a listener to these talks myself, the questions are often more interesting than the talk itself. So I'm very happy to take more questions. I think that would be useful.
They are always properly fitting to the audience interests. It's great. We have a continuation to the complex systems questions.
Yes.
By Swanit. Which actors do you think would have access to such complex systems interactions data? Facebook, Google, WHO, or large governments? Or
well,
more actors?
I think, well, the answer would probably be yes, they have access to it. Yes, so WHO, for instance, just to stick with the epidemic example, has access. However, the problem with these specifically government statistical data is that it is usually poorly collated from many different sources. We all know this now from the Robert Koch Institute's daily numbers, which are always off by a bit, and then, oh, it has been weekend, so we haven't received this data yet. So that would require an approach which is robust across missing or bad data, which statistical relational AI is. So it would actually be able, and very much unlike classical symbolic approaches, which would get hung up on the fact that there is a mistake in the data, be able to use that sort of data. That is true. And I do think, I mean, social network analysis is, of course, a huge field, and there are many, many, many other also deep learning supported methods there. So perhaps things should be a bit pure network data is presumably potentially not the most complex, sufficiently complex. Having said that, there is, of course, the connection to knowledge graphs that Professor Tresp will talk about really shouts out at one here, because a knowledge graph has the same general network sort of architecture, just that it's multi-relational rather than just having one edge relation.
So, thank you for that answer. Following up, I have again a question of my own on the large-scale deployment of artificial intelligence system in actually real-life context, because Jack Ma, the founder of Alibaba, actually said a few years ago he expects in 30 years we will have AI politicians and CEOs and doctors, all the positions where difficult decisions and unbiased decisions have to be made will be replaced by AI. But at the current moment, all the artificial general intelligence is mostly tested in games. So we have the deep learning networks that excel at Go, or video games, Dota, and now statistical relational AI that can play bridge. But do you believe that in the future, these will also be able to be implemented in real life problems? Will they hold up outside these very strict bounds that games often have?
Yeah, thank you very much for that question. I think actually statistical relational AI is probably as untainted as any from this gaming connotation, because it has a huge background through symbolic AI and explainability constraints in medicine and biology and biochemistry, which are high stakes contexts. I would like to just briefly, since we're talking about large domains over and over again, just quickly go back to what I am doing here and how my work fits in there. So if we take, for instance, such a proportional dependency network, and we assume that we are in a situation where this is appropriate, this is a semantic condition, in my opinion, that cannot be gleaned from data but has to be decided by the user. If we're in a condition which is appropriate, we can compute very efficiently, actually, in time only dependent quadratically on the complexity of the formulas. So very quickly, we can compute the limit network. This network, which as the domains get very large, this is what it will come up to. And this is even human readable, and it's easy to see, and so on. And yes, this could be directly used on large data sets. So the problem with large data sets would, in these contexts, no longer really be an issue. On the other side, then, the problem would be medium large data sets. Too small to be considered generically huge, but too big to be actually tractable. So at least we move the problem down to medium-sized sets, while for large data sets, we would have these asymptotic guarantees. And there's work on what is called projective frameworks, where a talk has been by Professor Jäger in Munich some weeks ago, where actually it is completely independent of domain size. But this has very strong constraints. This requires strong constraints on how our network behaves. But in my opinion, this, more than any improvement in algorithms or computer architecture, in order to tackle large domains, you cannot ground. That will not work on very large domains, and you will need to understand limit behavior and this asymptotic behavior. And that is unique to statistical relational AI. Pure statistical AI doesn't actually have that because it does everything propositionally. So this is also a unique chance of statistical relational AI to be able to work with these huge domains through limit processes. And I think that must be the way to go if we want to work on massive domains, as in big data size domains.
Thank you. We have one last question by Felix on Slido. When you actively imbue external inexact information like epidemiological equations into the framework, how will it handle contradictions in the knowledge?
Actually it does that reasonably elegantly because it is a probabilistic model. In a classical symbolical artificial intelligence model, which does not have any special approach for this, just a standard Prolog program or similar, this will just explode. It just won't work. Here, because everything is probabilistic, they will just cancel each other out in a sense. If you have two contradictory informations, with each have a certain probability associated with them, they will just be seen as opposing influences. And these opposing influences will all be factored together and will lead to a single result. I mean, there are other approaches to do this. So there are sort of purer approaches where you have a two-layered one. So you say, this is one model and this is another model. Each of them there's a certain probability that all of these things are true and a certain probability that a whole other group of things are true. And each of these are consistent. And then there's a probability that each of them is true. And then we reason from them. So that would have a weak probabilistic element to the symbolic AI. But in a strongly probabilistic statistical relational AI, they would just cancel each other out and extend as factors.
Thank you. So for the last minute, would you like to maybe close with a short commercial for your future lectures and seminars at the LMU for the students that are present?
Well, thank you very much. I will be giving a seminar on statistical relational artificial intelligence next term, where we go through all the actual technical work on it. And I will also give a general logic lecture, which should enable you to make your own progress throughout all these methods. Of course, my supervisor, my other Professor Brie, will also be giving a prologue course on symbolic, which focuses on symbolic artificial intelligence, which would also be of interest to some of you, possibly. However, I'm also always very interested in supervising master thesis or anyone who would like to work on this, either on one of the projects I've outlined above, particularly in the Bridge Artificial Intelligence project. There is still a lot of work to do, and this would be a hugely interesting project, or any other project or any situation where you believe complex reasoning and probabilistic reasoning might be helpful. I would love to hear from you, and I would love to assist you in how statistical relational artificial intelligence could help with problems you are interested in, or even you could help with, for instance, the Bridge or any other project that I am working on. And yeah, I think our research group is always ready to change direction, to move, to expand according to what the student members are interested in.
Thank you very much. You've also received thank yous and virtual applause in the YouTube chat. Now, for everybody, this was our first talk. We'll come back again in 10 minutes with our second presentation. We hope to see you, Dr. Weitkämper, later again in our socializing session too, on Discord after the second talk. So we'll be back at 20:20. Bye-bye.
Thank you very much.
Okay, so now we will continue with our second talk by Professor Tresp. Yeah, Johannes, the floor is yours.
I can already take over for the introduction. Professor Tresp, we are very happy to have you here. Thanks for joining us. You are originally a physicist. You did your diploma at the University of Göttingen and then went to the States, more specifically to Yale, for your master thesis and PhD. There you got into contact with the first imaging groups, and then you quickly started to work at Siemens in the machine learning field, and there you've been since today. So in 2018, you actually earned the honorary title of Distinguished Research Scientist as the first person on this planet in Siemens. And you're really true to the title, being in a major company, one of them probably the biggest AI player in Germany. But you're also a very active researcher. You are already close to 200 publications and have over 70 patents. Your interests, I already mentioned one of them, currently include deep learning, its health applications, cognitive models of the human mind and how we can model them using machine learning, and quantum machine learning. But your current and most prominent work in machine learning is on structured knowledge, which is mostly present in large graphs that include knowledge which we want to use to actually make decisions and use it in our artificial intelligences. So today you will be presenting to us your current research and past research in the field of machine learning with knowledge graphs. We are very happy to have you here. Thank you for coming. The floor is yours.
Okay, thanks a lot for the great introduction. Also, I mean, I really liked the previous talk from Felix. So I'm really looking forward to having many interesting discussions with him, because in the past you either met somebody from machine learning or from logic, and but very rarely somebody who has some understanding of both fields. So I'm really looking forward. Also, interestingly, so I hear some noise. Is that? Do you hear that too? Okay. Hope you guys can still hear me. So, so yeah, when I was at Yale, I shouldn't tell you how long ago that was. It was, in fact, sort of the last ages of the first classical AI wave, and there were people like Roger Schenk and McDermott there, and I knew some of their students, and most of them didn't really finish their PhDs. But I started off at Yale with a physics type project, working on small bubbles, and these guys were tracking AI and intelligence, and I was very impressed. So it's sort of a large satisfaction that I'm now doing this, also AI. These guys went to completely different fields in the meantime. So that's for me, it's a very interesting story. But I had always appreciation for the classical logical oriented AI, and I spent probably half of my life explaining to people from databases and that machine learning is interesting, because databases is closer to relational stuff, is closer to logic. And a lot of people at Siemens have database background, and for many years they didn't have any understanding of machine learning. But at the same time, I try to convince the machine learning people that logic and first order logic, reasoning, knowledge representation has something to say. And yeah, I'm also very happy that we applied for this ALICE program, which is sort of a big thing at ALICE. So ALICE is this European effort on machine learning AI, led by MPI and Bernhard Schölkopf. So a program is really a big thing there, and it will be on semantics, symbolic, and interpretable machine learning, I think, or AI, one of the two. So that fits completely into also Felix's interest. my general statement would be that yeah, I think cognition is important, the cognition view, because it tells you really what we are doing, ideally, or whatever, of psychology, cognition, whatever you want to call it, neuroscience. And how much, I mean, I argue that we are quite good. Some of us are quite good at logic, but it's something like intelligent people, intelligent beings like humans learn pretty late. Animals probably cannot do it. So it's sort of the most difficult thing, but we are good at certain things. We can follow rules. We can, some of us can do mathematics and so on. So it's there must be some reasons for survival to have these skills, but maybe it will take the next 5 or 10 or 20 years to really figure out a lot of these things. But in the machine learning community, there's so the interest is sort of awakening. A lot of efforts. That's why we call it semantic, symbolic, and interpretable. There are a lot of sort of activities which are quite interesting. So I think we will have interesting things, interesting initiatives and lines of research in the future to look at these two sides of sides of intelligence. So can I just make sure that people still hear me? Can somebody confirm?
Yes.
Okay, great, because you're always talking to the screen, and you never know if I don't want to talk 40 minutes to the screen, and turns out that nobody could hear anything. So, okay, so yeah, let's start on the talk. So, yeah, these are the great successes of deep learning, convolutional deep learning for images, recurrent deep learning for sequential data and translation and speech recognition, reinforcement learning for optimization and games, then the GAN models for these image transformations, and then more on the technical basis, embedding, representation learning, attention, graph neural networks. And we also have a more or less an understanding why it works. We have more labeled data, deeper models. Of course, nobody really knows why it works, but it works. New algorithms, end-to-end training that we are really optimizing for the task we are interested in. No feature engineering. And then it's amazing computational power compared to earlier decades. And it's amazing community. The students are all teaching themselves. They're exchanging, they're active, they're reading blogs, downloading code, experimenting. So it's a really different world from before when students didn't have so easy access to the latest research. But there's also the other side, data and deep facts and knowledge. So IBM Watson worked because we had this huge document repositories available. In autonomous driving, we need maps and GPS systems. In industry, we need big data or IoT, so Internet of Things. In healthcare, detailed patient profiles, and maybe many of them to be able to learn something. And then for humans, web content and Wikipedia, and I would argue for machines, the knowledge graphs. And so here's my my motivation for machine learning people to convince them that this is interesting. For knowledge representation, knowledge people, this is of course trivial. But the world consists of constants, things, entities, whatever you want to call them, and predicates which specify the relations between things. So there's Jack and Mary, and Jack likes Mary, and Jack looks at Mary at time t, so there's also a time component. And if you've never seen a knowledge graph, here in the middle you see one. There's Albert Einstein. He's a physicist. The physicist is a researcher. Albert Einstein is born in Ulm. Ulm is a city. Ulm is in Germany. Germany is a state. And there are subclasses and so on. And it looks quite simple. And it is simple, and that's really absolutely important because in the field of knowledge representation, people like to find all sorts of ontologies, but they didn't really worry about any instances. And the knowledge graph is sort of the opposite. It's all instances and very little ontologies or schema information. And that's a start state, and I think that's extremely important that we are looking at this now from this perspective, and maybe in coming years we have other things creeping in again, more fancy background knowledge. But this intermediate step, let's say, was really extremely important, because anybody can follow this. This is a really link between knowledge representation and all the other areas. So there's we're looking at this as the temporal knowledge graph. So entities are nodes here, obviously, and a link exists if it's true, and there can be also timestamps, so it doesn't have to exist at all instances in time. So we can have a quadruple SPOT with a timestamp. Then we call it temporal knowledge graph. If we only consider the static statements, then we call it a knowledge graph, simple. And here's Laplace. So Laplace's daemon is one of the big goals I'm having to sort of describe the world at this human abstraction level. And there's some really, I think, interesting stuff to be done here. But let's look at two initiatives. So I try to put them on the same level. Anyways, I think for me, the real breakthrough was the Google Knowledge Graph, because technology, everything was there. They didn't invent anything new. It was more that they took things away. But before the efforts, which were quite valuable, like semantic web and linked open data, but it was never really clear that this ever could work robustly, and if people could really maintain all these databases. And Google then showed that it can be done. Nowadays, they say they have about around 100 billion facts in their knowledge graph. They have very good fidelity. They figured out how to maintain it, how to keep things up to date. With considerable effort, considerable also human effort, although they are not very open about a lot of things. And it's useful. They showed that they use it in search, question answering, text understanding. And if you listen to the talks, it's really embedded in many Google applications. So they really showed the world it can be done and can be made useful. And Siemens also, partially thanks to me, was really early interested in this field. And there are many projects at Siemens doing knowledge graphs without learning, let's say. So here on the right side, you see a little bit how Siemens looks at it. There's this knowledge graph hovering over the city, and the knowledge graph knows everything, can help you writing tenders, can help you replying to tenders, can help you understanding your supply chain, analyzing service reports, helping you in your repair, and so on. And so I always say knowledge graph is not the magic bullet, but it is probably the right technology. And that's why I also had here not just a hype. I mean, whatever you call it, I don't care what the name. You can also call it multi-relational data or something. But this seems to be something people converging to from different domains. And I'm pretty confident that this will be a stable thing. So I don't care too much about the name. And here's another example. A person goes to a university, more like a social network, has a brother, plays football, has a job somewhere. And then, of course, you can link it to web pages, text, videos, and images, and you can enrich the whole thing even further. Yeah, so I already showed this one, the supply chain management, maintenance, repair, and we have a team of probably 30, 40 people who are doing all sorts of applications within the company. So it is quite a popular project in our unit. We have another 40 people doing machine learning and NLP and even more. So these efforts are quite sizable. And so in my team, we always looked at it. So I'm originally from machine learning, and I always looked at everything like from a machine learning perspective. And we were, I think, the first team to develop a serious machine learning embedding approach in this domain. So the idea is simple. So a triple, which the knowledge graph consists of these triples, SPO, has 3 indices. So you can map everything to a tensor with 3 dimensions or modes. And So so one index is for the subject, one for the object, one for the predicate, and if the SPO is true, we put a 1 here in this tensor. Otherwise, we leave it empty. So it's huge but empty, but pretty sparsely populated. And then we factorize it. That was the original idea, and then we get one matrix out where every row corresponds to an entity, and this is then the embedding or the latent representation of the entity. Here's for the subject, for the object. These matrices are really the same. And then we have one matrix for each relation type. And if we want to make a prediction or an evaluation, we simply take the embedding of the object multiplied by the corresponding matrix here of the relation type, and then with the subject representation, we get a number out, and we consider this to be the confidence that this statement is true. And if a 1 wants to become a 0, then maybe it's a mistake in the database. If a 0 wants to become a 1, it's something we can, with some confidence, predict to be true based on the patterns in the database, in the knowledge graph. And since then, so this was 2011, other groups developed other models, Dismold, complex, multi-way neural networks. Trans-E, the family of Trans-E models is quite popular. And more recently, graph convolutional networks, graph neural networks, graph SAGE. But they are stronger if you only have a single relation type. We typically have many relation types, but in social networks, for example, nose is a single relation type. So they are very strong there, but we are open. We are not limited to just our own models. We do whatever works best in a way. So this is, the same picture again. And it's a form of representation learning, because you can think of, if you evaluate Max likes Mary, you map Max to Max's latent representation vector here, likes to latent representation vector, and Mary to her latent representation vector. And then you have some sort of evaluation scheme. In the tensor approach, it's a core tensor, and what you can also use a neural network. And then you get out this probability of the statement. So it's important to have this idea. I mean, that was one of the breakthroughs, I think, in deep learning, that this idea of representation learning or embedding learning, that discrete entities like Max and Mary are represented by embedding vectors. We are also using that. And we also got it to work in some projects. So this is the closest thing Siemens gets to a social offering, a social network offering, consumer offering, because we are not really doing consumer products anymore. But in the automation framework, we are context, we are world market leader, and the solution might contain 100 or 1,000 components. So we have 60,000 active users per month, which is quite a good number for Siemens for this type of product. And the goal is essentially to build a recommendation engine to support the user in selecting items. And here on the right side, you see the knowledge graph. So the items are these white nodes here, item 1, item 2, and then solution is sort of the buying session. And here's the important contains relation. Solution 1 only contains item 1, solution 2, item 1 and item 2. And then we also use other information on this item. For example, it belongs to the family S7-1500, and it's a type of a controller. This one is the voltage 24 volt and is a type of a plug. And by adding this additional information, really got better results than the standard matrix factorization approach. So here the RESCOM is the model they developed. So Marcel Hildebrand was here the leading person. And so this hits at 10, which means that the true item the person had been chosen was in the top 10 of the ones we suggested. But okay, these numbers are difficult to interpret, but also what is important is that I mean, the model needed to be very fast, because at the moment somebody does a selection, this must be taken into account for the next prediction. And of course, we want to be able to enter new users or new solutions, but we also want to be able to enter new items, which is called a cold start problem. And also here, this is, in fact, we were using our own invention, the RESCAL model, because these operations are very efficient in these models and can be done quite quickly, whereas other models require a lot of post-training. So, and not only do we have good numbers, it's also real life. So it's being used by people, and we are collecting data currently, and hopefully at some point we will do a next versioning. We get see how satisfied the customers are, and we get, of course, new data to refine our model. So we are quite proud of this, because it's also for us pretty rare that something so quickly becomes a solution and it's actually being used. So that's nice. So it's also useful. But we are not just using or looking at these factorization approaches. We are also looking at paths in knowledge graphs, because they give you a better explainability component. You know? And so if you say to your user, so we recommend this item, and we cannot explain really why, it's not always good for all applications. Sometimes the user don't care, sometimes they care. And paths in the knowledge graph sort of can be looked at and analyzed. No? And here it was formulated as an argumentation game. So there's one agent always in favor of the statement, and one is trying to argue against the statement. So here, for example, Richard Feynman, nationality US, that would be the query triple to be analyzed, and then the agent one, who tries to support this triple, found that Richard Feynman lives in Queens, and Queens is in the US, so he must be a US citizen. And the other agent, the counter agent, says, but he's Russian, because his parents are actually Russian. So it cannot be American. And then the user can look at it and think, oh no, I believe this one is true. So he has some explainability component. Or Nelson Mandela is an actor. Of course, he's not an actor. So the pro tries to say, okay, but he's friend of Naomi Campbell, and Naomi Campbell is a friend or has dated Leonardo DiCaprio. And the contra against this argument is, oh no, he's a lawyer, so he cannot be an actor. And interestingly, these are, in a way, they are instances of rules. They're not the rules. The rules are in your head. No? So you're making up the rules in your head when you look at this, which I think is also a very interesting cognitive aspect to this. No? Maybe we're not aware of all the rules we're using, and it's more an implicit thing. And in practice, it's quite complicated. So, I mean, this is the success of end-to-end training. You build this really amazingly complicated models with agent 1, agent 2, and here the judge who tries to evaluate who's right and who's wrong, uses recurrent neural networks, LSTMs, uses reinforcement learning for the adaptation, and so on. So it's pretty complex, really, which can, also be a problem by itself. And here's one application we're actually doing. And here we, so this might be interested to Felix, we are including rule patterns. So the goal is this drug repurposing. Now, because if you have a drug which is already approved for some disease, all the side effects are known, and you can use it for another disease without going through all these testing phases. Remdesivir, I think it's a current example for the corona. And for this, so here on the right side, you see a little bit the data, genes, diseases, symptoms, pathways, and so on. And we applied a similar approach to the one I just described, but we also included rules, which we got from some paper, as sort of a guideline or something like a positive constraint that we want the solution to be to follow these rules in a way, in a soft way. And in fact, the approach got best results compared to other ones. So here's an example, a simple example of a rule. So if a compound treats a disease and the disease is similar to another disease, then maybe the compound also treats this disease. So I should really have different symbols here. And then, so it means like if sorafenib treats liver cancer is similar to a kidney cancer, then it should also treat kidney cancer. Of course, most of the actual rules are more complicated, and our approach is essentially a learning approach. so it just takes these sort of rules as a soft encouragement, a little bit like in Markov logic. And there's some possibility of evaluating our results by looking at clinical studies which are being performed, and sometimes they sort of follow what we recommended. So it means that our database and the thinking of the doctors or the experts came to the same conclusion. And yeah, we are in contact with our clinical people to see if they're not interested in this. So this was so first I started with factorization, and then now the path analysis, which gives you more of an explainability component to it. And we're also looking at the temporal dimension. So triples can be true or false at different instances in time. And the first approach is in a way quite simple. So we just add a fourth dimension. So we have an SPO and then T. And then we have a 1 if at this instant in time this triple is true. And in fact, we're using that idea in a lot of medical applications. And it works quite well, but in sometimes it's not a suitable application. And they are essentially, we're working with representations of entities which can change in time. As I mentioned before, we have these embedding vectors or these latent representation vectors, and they can change in time. And then we have another type of a predictive model. And we also need some fancy statistical models here, the Hawkes point process, which is a generalization of a Poisson process. But essentially the advantage that we can model it with LSTM here, so we get more fancy predictive models than with a simple Poisson model. Also here, the modeling is quite complex, also LSTMs, everything. And we applied it to a data set called GDELT, a global database of events, language, and tone, and another one, ICEWS, Integrated Crisis Early Warning System. And the task here is to provide early warning on conflicts. So these are data about different countries and how they interact, and if they trade each other, or if they attack each other, peace and war, and other types of relationships. And it's an actual program or an actual activity where the data is actually filled constantly. Yeah, we got a good results because we also got I think it's hidden in this window, best paper nominee at this AKBC conference, which is quite nice. And we are thinking of a lot of Siemens application, modeling events of streams in industry, mobility, energy, and healthcare. These type of event data are quite common in industry, and we are currently trying to find the right type of application for this technology. Let me see, I'm doing a time. Okay. So I should probably be a little bit shorter on the healthcare part. So we looked at, we did a study here a while ago analyzing the big data issues. At that time it was called big data digitalization. And then we did some projects essentially where we integrated clinical databases into a learning database with our learning model. And there we sort of encountered the difficulties of integrating data in a clinic or in any enterprise. It's a story, and everybody sort of makes the same experiences. Quite difficult for several reasons. Eventually we ended up with data which are also used in a clinical study. So there was a good quality in the data, which was quite nice. And so we always look at everything which is structured data as being sort of knowledge graph data. So for example, your age, gender, preconditions, tumor, primary tumor. So these guys had, these women had tumor already, history of metastasis. Then we have information about what happens in the clinic. And then we are doing two things. Either we are predicting the decisions of the doctor right away. And for example, in a tumor board, there is sort of a very definite decision point of view or point in time where all the data is brought together and the doctors make decisions about the treatments. And then we're saying, okay, let's copy or learn about all the information the doctors know, why they are very smart people. And then we get a committee effect because we are modeling many doctors and not just one. So this can lead to an improvement. And the second one is endpoint prediction, where we are predicting, for example, how, if the cancer goes away, if it gets worse, how long it takes to get worse. So progression-free survival time is something we are modeling. And from both, of course, you can derive decision recommendations. If you immediately predict decisions, you have a predictive model which gives you a decision recommendation. Or if you model the endpoint, then you would suggest a decision which seems to lead to the best endpoint. And now we even have ways to combining these two approaches in a very elegant mathematical way. And we are quite proud, and I think that's a very recent paper, which I think is going to have some impact, because we can also evaluate decision models now without saying the clinic has to use our model, which would be very difficult and impossible from an ethical point of view. So we are working with data here, breast cancer data from Erlangen, nephrology, also kidney disease from Charité, and eye clinic here from the LMU. And here, so this is a really nice evaluation approach. So essentially, we can, of ethical reasons, they cannot say, please doctors use our system, and then we see what happens. So our medical expert was quite smart. He said, let's take, let's say, 5 real doctors and have them look at the data and make a decision recommendation. And the 6th doctor is our system. And then, of course, most cases, everybody agreed on the treatment. But if there was disagreement, then they favored our system and didn't like necessarily what their colleagues were suggesting. So that gave us a lot of confidence that our model, our approach is doing something useful. Because in machine learning, of course, you get good numbers, but you never exactly know what these numbers mean. And this is actually a study we are currently extending and want to make it more solid statistically. So, but it gave us a lot of so I want to maybe skip this because you're probably also already sort of getting tired. So yeah, we are looking at different issues: missing data, explainable AI issues. Can we explain our decisions? And this is what I just mentioned, sort of the combining outcome information and decision modeling in one approach. So that's quite nice. Yeah, I also like to add this now because, of course, Siemens Healthineers, independent of us, is a very strong in medical data analysis and medical imaging. And if you look at this as time and this as complexity, then you start with pure image reconstruction, analysis, measurement, maybe defining abnormalities and findings. And the issue is, I mean, they can do this at, let's say, at Siemens, but if you go into this direction, you have to do expensive medical trials, and so you try to shy away, and you try to claim everything is sort of an improvement in image analysis, no, in visualization. So it's just an improvement in visual analytics, and not so much telling you what diagnosis is true or what treatment is true. Yeah, there's so I like this proverb from Goethe, or you see only what you know. So if you don't have any background about, I would say if you go to Rome and you say there are all these buildings which have fallen down and nobody's cleaning up the city, what is this? No? But of course, if you know all the history of Roman Empire, you have a very different view on what you're looking at. And the idea is to use this knowledge graph, or here it's called scene graph, to understand images. So not just detecting cats and dogs, but for example, in this case, a person is on a motorcycle has a wheel, a person wears a helmet, person wears a jacket. So this goes in the direction of giving you a much deeper understanding of what's going on in images. And you can consider it a scene graph or knowledge graph. And if you and the idea is to find these bounding boxes which define where objects are, then classify this object and also detect the relation. So this would be the subject, the object, and then the predicate is next to. So the person is next to surfboard. And it turns out if you only do it based on image analysis, it doesn't work very well. So we designed this background knowledge graph based on the annotations in the training data. So a person can ride a bicycle. A bicycle has a part handlebar. It's on a road. A building can be next to the road, and the bicycle has also a handlebar and a wheel, and so it's very likely that a person can also ride a bicycle. So in other words, you cannot just take whatever was in the training data. We also have to do some sort of inference to conclude about things which were not actually observed in the training data. So we needed our machine learning aspect in this knowledge graph generalization part. And if we add this knowledge graph to the visual process, the improvement really improves greatly. And I mean, Stanford, the people who supplied the data, they did something where they took text data as background information, and we were better with our approach, with the knowledge graph modeling approach. And also the Stefan Bayer, who did this, won the Best Student Paper Award at ISWC, and was Ishkai Best Paper Award track as well. So it was really nice success. Here's some examples. So this is a person next to person. So so we discovered this correctly, or truck on the road, or lamp on a box. So this is a mistake. Motorcycle is wheel. It's correct, but it's the wrong wheel. And here, so this is interesting because this is zero-shot examples. These are triples which are not in the training data. So bus next to bus. So ours is the last approach here. So all the approaches were successful here. Tree behind bear, we were successful, but the V-trans-E was not successful. Laptop on stove, we got it. The other two approaches didn't get it. And bear rides motorcycle, nobody got it, but I would say, of course, it's a person in a bear costume riding a motorbike. So, yeah, so we are smarter than the annotator. We're extending it to videos, also to more recent developments in machine learning and deep learning relational transformer networks. And finally, I want to also address the cognitive aspect. So we think this modeling of knowledge graphs and tensors can be related to the human memory systems and perception system. So and there's this interesting transition always, that perception and memory is not just on the subsymbolic level. We just don't have like a sort of some image memory. We can also talk about it. We can talk about what we're seeing. We can talk about episodic memory, what we remember, like what happened last Christmas, or facts, which is semantic memory. Munich is in Bavaria. So there's always this immediate translation into something we can talk about. And this is also confirmed by the way people in cognition think about the memory system. And we think that's what we are doing here, for example, in the vision part, is not so far away from that. So let me show you this architecture. So I'm not sure if it's can be understood in the little time we have here, but essentially we have sensor information. So this comes from the visual centers, and then we are postulating there's this representation layer which takes over a large part of your brain. So this is where something colors are represented, or sounds, or movements, and this is pretty global. And then there are local indices for concepts. So this would be like in the so-called parietal cortex. This would be in the temporal cortex. And people find these indices, and we're suggesting there's this interaction between these representations and the indices, and there's a mirroring. So if we so this would be simply a deep neural network predicting some entity, and then the entity which is detected, the brain is told about it by this feedback connection. But then we also need a memory layer to memorize what has happened before, for example, to decode triple information. And we need an index layer for instances to memorize past episodes. and also a semantic memory, which tells us about things which are independent of time. And it fits to some degree to some theories about consciousness from DeHaen, for example, who also postulates a bottleneck processing. So this would be our bottleneck here. Everything has to go through the representation layer. But also, if you think about language is a sequential process. So I mean, a lot of things goes on in parallel in the brain, but there are also some things where we would also agree with might be quite a serial and bottleneck character. So that's something we are working on. This is how we think it's organized in the brain, or this is general knowledge which fits to our modeling assumption. Here's the visual cortex, then we have sensory memory. The representation layer would take over a big part of the brain. Here, index layer is in the temporal lobe, and working memory is sort of assumed to be in the prefrontal cortex. And we get models which are quite competitive to leading models. So, I mean, we don't want to have the best possible model. That's not our goal. We want to have a very good model, which is also biologically plausible. And I think we are going in the right direction here. So this shows you that what I mean by index layer and representation layer. Of course, in the cognitive and brain sciences, few things are really agreed upon by everyone. It's as small as 80-20 thing, or 70-30 thing. So maybe 80 or 70% agree on something, but then 30% would completely not agree. But this is a Nature paper, quite famous, from Quiroga and co-workers, and he found these neurons which are very selective, in this case to Jennifer Aniston. Sometimes they're called Jennifer Aniston neurons. So this neuron here fires only when there's something of Jennifer Aniston in the visual input, or if somebody talks about her, then this neuron fires, and it's not responsive to anything else. So it seems to be very specific to this one person, and they also found other ones, Halle Berry neurons and others. So that's as I said, this is not clear how to interpret it, and there are different people who interpret it in a different way. But in the extreme case, these cells are called grandmother cells, which means you have one neuron just for your grandmother. In this case, you would have one neuron just for Jennifer Aniston. But nobody really claims there's only one neuron, but maybe a small number of neurons. And this would be our what we call indices. And then here's the representation layer. So that's another Nature article from Hoot and co-workers who looked at semantic. So they read stories to people and looked which brain areas are active, and then they tried to map the semantic content to the different brain areas. And as you can see, they put them everywhere in the brain. So this would be our interpretation of a representation layer. Where sort of meaning is represented, and one example is always the top. The top can be a bikini top and can be on top of something, and the word top has two different representations based on the semantics. No? So it's not the top word; it's the top semantics, which is important. So that's why I mean it's not. No, it's plausible, I would say. No, it's not. We have indices in the temporal cortex. We have representation layers. So there's some. It's not completely out of the blue. Before we brief, this is I think more or less the last slide. So we mentioned quantum computing, and we are actively doing something here. Yunpu Ma, who's a student who's very knowledgeable here. He developed, in fact, 3 algorithms how to map knowledge graph calculations, inference tasks on quantum models. It's not something you can which will work in a short future shortly. There are some things which are not so nice. For example, these QRAMs are still a very big challenge for quantum computers to implement. And these are more conceptual papers of some ideas how things could be mapped to quantum circuitry. But we just presented it this week at a physics quantum workshop. So I think it's an interesting direction to go into, and it would, I mean, the scalability issues in terms of the size of the knowledge graph and the size of the representation. So if you have a very high representation vector, sometimes you get into computational issues. And we also applied for a funding project from BMBF with some partners. So that's something we want to continue to explore in the future. Also to see how far we can get in this direction. So I think as a conclusion, there's a lot of potential in combining deep learning with machine learning and knowledge graphs. For me, knowledge graphs, and however you want to call them, is an extremely basic thing in the world, very basic and important representation of information. And I hope machine learning community, deep learning community will look more in this direction. And as we're seeing, I mean, we're proposing this Alice Alice program. So we have one national funded project where I'm the consortium head on machine learning with knowledge graphs. And we are also involved in this Alice lab, European Lab for Learning and Intelligent Systems. And there will be a Munich node, and it should be announced any day. And I'm on the faculty of this Alice node. Then I'm co-director of this Alice program, which is proposed. Again, maybe hopefully in 1 or 2 weeks, we will get the confirmation that this can be realized. And a lot of people Felix mentioned are also part of it. Luc de Reet from Belgium, and Muggleton, I think he's Imperial College. So that could be a really interesting place where we can change exciting ideas. And we also part of this ELISE program, which is connected to Alice and provides funding for some of these activities. So I think that, I mean, I'm really happy that Felix is here to have really interesting discussions because there are not too many people who understand both sides and have a good understanding of how people think in the different fields. And as I mentioned, I mean, our Alice program shows that, and also if you're looking at what's going on in the field, there's some excitement in this direction. So I'm pretty much focused on knowledge graphs, and other people looking at other issues, also explainability, of course, in extracting rules or integrating rule-based knowledge in learning. But I think as long as the mind has to be open, that would be my conclusion. And I'm convinced that we should look more closely on how human intelligence really works, because we can do a lot of these things. And I'm also convinced that anything our brain can do, we can also at some point do in a machinery. It might take a long time. But since we are able to do logical reasoning to some degree, at least humans can do it, there seems to be a biological reason for that. And we should be able at some point to make use of it in our AI systems sometimes in the future. And you guys are all very young, so it's good that there are open questions and not everything has been solved. And yeah, I think you're looking into a bright future. Thank you very much for your attention.
Thank you very, very, very much for this incredible talk. Also incredibly dense. There are so many different parts that I personally would like to ask into more detail. Slido is now again open for you to pose your questions. Also ask about all different aspects that were addressed in this presentation. As a starter, maybe I have a question that interests me really. Based on your focus on cognitive abilities of the human. So your model is based on different kinds of memory, if I stand correctly, that we then reason on and where we can learn new facts. So do you believe that with this model, really all the human cognitive abilities are covered that are necessary for human level intelligence?
No. Finish. So no, of course not. But I mean, also, I mean, there's a lot. I mean, often a lot of these discussions, people really fight at each other. It's because they're talking about different things and different issues and different everything. So I think, for example, animal intelligence is something we should also consider, and humans are really the absolute top of the line of the development. So some of these things are probably so. For example, I would think a lower animal has some episodic memory, compares it to past experiences, what he's seeing, but maybe not on this symbolic level, maybe more on this experience level. Or I noticed this before. Then maybe relations became important for social beings, where it was important to know who is the head of the team, head of the pack, and where something is located. And so that might be whatever animal, like wolves or something. Like herd animals have a certain intelligence, and then humans, and also in humans. Now you can also distinguish. I mean, I don't know if like an average person in the world in some whatever island or something can do math or logical thinking, or maybe some fundamental form, but he's not really trained or educated in some of these things. And sometimes we are comparing the best of all humans to our AI system, and that's it's not always fruitful. No? Of course, I mean, that's how it started. No? We started in the whatever people started in the 50s, 60s to think, okay, if we understand intelligence and logic, we can immediately build much smarter systems, and it was probably a reasonable first approach. And now people are. I mean, some people say, you know, there's a pyramid, and we have to build the different layers before we can really address the top of the pyramid. So I'm yeah, whatever. I mean, there are from all the models which exist, I am very convinced about my model, but I never would claim that it solves all the issues in intelligence. But it's our, let's say, our approach to it, and we want to see how far we can get it, can get with it. But I mean, the human brain is simply so absolutely amazing, and we are already so much smarter than a dog or something, and a dog is already quite smart. So we have to look at these different levels of intelligence and not always say we have to beat the smartest human immediately. No? I mean, it's sort of interesting that we can do it in some games. They seem to be smarter than the best human player, but for many issues of intelligence, that we should really distinguish these different levels. No? And I might be on the level of some whatever animal, but definitely not on the level of human intelligence. No? That's still a lot to do.
I believe that.
Yeah, but I don't think, I mean, maybe I'm disagreeing with Felix. I would not think that logic is like the people are so good at. I mean, okay, sometimes we are also just imagining things. We're playing different scenarios and then deciding which one is more plausible. We also have this logical. I mean, if we do mathematics without logic or logical understanding or detection of contradiction or something, we wouldn't go very far. So we definitely have some of these abilities, but they might be very specific to humans and very specific to some small set of things we have to do as humans. So I know that. So I see a spot there for logic, and definitely, but it's not 99% of our intelligence. It's 10% maybe, I would think.
Okay, we have another question regarding the cognitive science models from Swanit. Regarding the cognitive science-oriented models, what are current drawbacks or shortcomings, and what kind of improvement are you looking for next?
Yeah, I mean, sometimes I show the slide. I mean, there's this. We also read some, in fact, some cognitive literature, some neuroscience literature. So there's some people like Graniga, what's his name? He wrote the big textbook in the US on this, and it's a very good book. He has this. He says the brain seems to consist of 1,000 or maybe even 1 million modules, and they're all doing their things, and they might all be sort of different. And the amazing thing is that all of this converges to one decision. I mean, the brain can think many things. Who cares? But we can only do one thing, so it has to converge to one interpretation of reality, and then we can act on that. And that's a big mysterium. But most people are convinced that there are these many different modules. And they might come to different conclusions about the current interpretation of the world, and there must be some very fast way of that the brain agrees on a clean interpretation of what it's seeing, and then sometimes you notice in these optical illusions or some other cases that there's some different ways of interpreting a scene, and it's very irritating. So the brain probably tries to avoid that as much as possible. But also the positive thing is it's absolutely okay to work on these 1,000 modules, to vision and language and reinforcement learning and social networking and so on. For example, the brain uses surprisingly many resources to understand the social context of the person itself. So what to do to increase your social value, to have more social recognition from the environment. How do you know how to socially act correctly without offending people? That's something for social animals like human beings, and other animals probably don't care. If you're a tiger and a lonely tiger, you don't care about social interaction too much. So that's why I mean you can learn some things, not everything. I won't think everything, but you can get a certain orientation of works in the brain. So working on these modules and getting better in one of these faculties is absolutely fine. Of course, the one big challenge would be to see how can we get to one interpretation so quickly. So this idea of unconsciousness or whatever, that so much is going on below our level of consciousness is quite true. People agree. So the one book, I mean, there's also I don't know if you look at what Joshua Benjo is doing. He's also looking in this direction, and there's also this one book, Thinking Fast and Slow, which a lot of people are looking at these days. And there they make this distinction. So the fast thinking is our animal thinking. So anything we are doing without, which doesn't require any effort. So even looking at a scene and understanding a scene doesn't give us any headache. It's very easy for us. No? But the moment we have to invest energy in some thinking, mathematics, and so on, that's the slow thinking. And the goal of the brain is to make slow thinking into fast thinking, sort of to automate it. So your brain doesn't have to think about it anymore. And that's, for example, seems to explain, or it's an interesting level of explanation of certain effects you're seeing. So this type of cognitive literature is quite interesting, but who knows how far we are away? It might take still 20, 40 years, but the feeling is that there's some progress in some direction, I think.
We should maybe make an own meetup about the cognitive side of things, and also invite cognitive scientists from the LMU. I mean, we have a strong center there.
Yeah, it would be interesting. But I mean, my comment would be, I mean, there's the brain, there's cognition, there's whatever, and divide all these things by 100, then you have 100 different subfields, and they don't necessarily like each other or talk to each other or appreciate each other. So even it's not. I mean, it would definitely be interesting to see what they have to say. I would be also very interested. But the people working on so many different levels and so many different issues, it's just amazing. I'm trying to find also. I think there's some good people in Tübingen, for example, or I think it was Tübingen.
Yeah.
Who are thinking this direction. Of course, a lot of people doing a lot of like psychological experiments or working on and of course in LMU we have a very good, and maybe Tom also, very good brain science people. But I gave a talk, and the first talk was a couple of years ago, and I thought there was a good interaction and good ideas. The second time, it seems they are not really interested in this level. They want to do their rat experiments and look at the data and understand the data. So it's also not that. So it's this sort of thing. It's sort of segmented, which is probably also okay. But if you say let's talk to this one cognitive person, you might get very different perspective on things, whatever. But it would, I mean, I would encourage that. I would also be really interested to see what these guys have to say. And also now of course everybody looks at AI, so maybe they have. Before maybe everyone said, "Oh, you are AI, we are doing something else. Why should we care?" No? But now with all this funding and attention to AI, maybe also all these cognitive people trying to position themselves towards AI, and that would be interesting to see what they think about how they look at AI and these problems.
Yeah, we have another question on Slido by Swanit. We'll go slightly over time. He's asking, regarding fast and slow thinking, the book by Kahneman, how do you think could we approach the idea of creating reinforcement learning agents which can develop this kind of structure themselves from data?
Yeah, I mean, I think reinforcement learning is going on in different dimensions in the brain. So as much as I know, so don't claim to be the expert. For example, I think in Oxford, Cambridge, there are like Daniel Wolpert, and one guy is now at Max Planck in Tübingen. So they have been looking. Some of the people have been looking for reinforcement learning in brain sciences for many years. And for example, one is playing a tennis ball, so improving your tennis play. There's probably some reward and search and optimization going on. But then, for example, when I said before, this social interaction, that you have an internal reward. So the part of the brain and any intelligent system is to make something which is far away, local. So you cannot just say, if I do this, do I improve my social standing? That would be too far. You're dead before you know. So your brain needs to build up internal reward systems, which says if seems to be moving in the direction to increase my social value, I get an internal dopamine reward, and that can be considered a reinforcement learning issue. So on a very high level, social level, and probably reinforcement learning is going on different levels in the brain. But these are two I think which are quite interesting. So there's these internal reward systems, and they're often modeled in some form of reinforcement learning.
Thank you very much. I have a last question as the closing words, some kind of advice for young graduate students, which we have many present here. So it seems that you have very many different projects of very different natures, all handled at the same time. So would you rather recommend graduate students to take one idea and follow that for multiple years, or trying many different things until one really fits you?
I mean, the first answer would be, as a grad student, you should do grad student stuff. I mean, it's sometimes always this, we should prepare somebody for industry or something. I think that's the wrong way, because industry moves so quickly. Now, when we started with big data and told everybody we need big data, and the moment universities reacted, a lot of industry had lost interest already, and they did something else. So I think it's not a good idea. I mean, of course, you cannot completely ignore how industry works and things, but it's more important that you do the best PhD possible. And then my comment would be that different people with different who like to work in different kinds. One person likes to have this big, huge challenge, and maybe that would be extremely rewarding if this person solves this challenge. Other people want to jump around more. So in my team, so I'm working with 15 students. It's sort of, I mean, I didn't know that. I mean, until a couple of years ago, I maybe had 2 or 3 students, and I have no idea if this would scale up. But it scales up because of deep learning and because of all these communities and all this self-learning and self-training. And I think I have a very fruitful interaction with my students, but they can do things I cannot do, and hopefully I can do things they cannot do. So it's sort of a division of labor, and a lot of them are really extremely self-motivated. they get excited by the papers they read. I mean, nowadays it's for example, vision. I hadn't done vision in many years, and then we had this idea about this scene graph sort of idea, and and then I thought, how far is this away from me not knowing really anything about vision? But then a student came, he was ambitious, he was also not a vision expert. You download the code comes with the data, you sort of understand what's going on, you tweak a few parameters, and you have improved a world-class system without too many difficulties. So that's how you get very quickly very sophisticated works, maybe. Yeah, I mean, the best thing is to find your, I mean, it also depends on if you want to continue in academia or in research. So there are very different personalities, and everybody sort of needs to find his or her own way through academia and find their own motivation. So that's probably the best advice. Pick a good advisor, but also be ambitious. And I think if people have the feeling you are that you did really good work in your dissertation, then they're maybe not so interested in what exactly you did. But of course, yeah. If you're in computer science, I mean, you have very good chances anyways. If you go into philosophy, maybe it's getting more difficult. Oh, wait, okay. Maybe one more comment. I also notice, like in machine learning, for example, in terms of citations, the field. I mean, it didn't used to be. There was more other areas, but now in machine learning, if you do something reasonable, you get a lot of citations. Let's put it this way. So automatically, you have a pretty good citation record. In the cognitive science, this is already not so much. No? So even the pretty good people have much fewer citations, which might also be related to job opportunities. Although I'm pretty confident that at least academia will continue to be interested really in this, the two sides. Now, if you have a machine learning background and cognitive background, I think that's very attractive for many universities. But you sometimes you notice, maybe this field is really attracting a lot of people. And although a lot of people are talking about cognitive stuff, it's really a much smaller community, and the citations are not so high. So that's sometimes a little bit interesting to explore. No? But then the world. I mean, okay. Also, one comment I want to make is. I think it's not just a hype or a fad, no? Which doesn't mean that the jobs will not be hypey. No? So, I mean, this deep learning or this whole machine learning, everything is sort of embedded in the whole science. So there are people in physics doing it, in chemistry doing it, in bioinformatics doing it, and they're not doing it because they like a certain methodology. They're doing it because it helps them in their field. So this whole AI field is really embedded in all of science. But I have a huge confidence that this will continue and will continue to be successful. But of course, industry, for example, we have to be very quick when we start something. Because if you lose out on a business, then you have lost. But then maybe after a couple of years, some industries discover, oh, we don't really have a business model for the next year, so let's stop it again. So it might look that the jobs go down again for a while, but they will go up again. And in the long run, the scientific enterprise is definitely the right one. So I have a lot of confidence that even if it might look that the job market cools off for a while, it's the right background, the right technology, but maybe also not just deep learning and not just the tricks and not just the heuristics. It's good to have a background in logic or in cognition or in statistics or machine learning to have a broader perspective on things. But yeah, so yeah, I think it has a good, bright future, but it might be a little bit bumpy.
Thank you very much for the advice. I followed it. I want to go into research. And thank you very much for the talk again. You also got thank yous from the YouTube chat again. Now, the last word lies with our president, Natalia.
I'm on mute. Yeah, I was on mute. I'm so sorry. So again, thank you, Professor Tresp, for the fantastic talk, and to you, Dr. Weitkämper, as well, if you hear us. And also thanks to all people in the audience who watched us tonight. This has been really great. And now we will switch to the Discord server. Just a reminder, again, you can find the link below, so check it out, pick up a channel, or yeah, just check them out one by one. And stay tuned to our channels in the social media in order to get the newest updates, especially the meetup.com page. And we hope to see you soon at our next digital meetups. Yeah, take care, everyone, and bye.
Bye-bye. Thanks for inviting. It was really a nice experience. Thanks.
For us as well. Bye.
Bye-bye.